Here we're asked to express the given series using sigma notation and then evaluate the sums by hand or with a calculator. So honestly, this concept is a little bit tough to teach because it's a lot of like recognizing a pattern to see what's happening. And the more, again, as a math teacher, I see so many numbers that the patterns become fairly easy for me to find. But for maybe you, if you haven't like noticed the pattern as things are going up, it's much more difficult to find the argument or the expression that we're going to have in sigma notation. So really the only thing that I can recommend in this situation is try and get as much practice with these types of problems as possible because they get easier as time goes on. So one rule when I am doing these that not every teacher or not every math student follows is that I always like to start, like when I'm doing a sigma notation here, I always like to start with the index at 0. Now, not everyone has to do that, but it just makes things easier for me, I think, because then I can think of the equation, especially if it's like a linear function or something like that, like it's in slope intercept form. So what I mean by that for this first one, what I notice here is that the pattern is that it's going up by 4. It's going up by the same amount each time, which tells me it's linear because it has a constant rate of change or a slope. And my slope is going to be 4. And I'm going to multiply that by whatever the index is because that will give me my value. Now, the nice part about when I set k equal to 0 is that I'm always going to have a y-intercept at whatever the first term is. So in this case here, 4k plus 4 is going to be my argument or my expression. Now I just need to figure out what is the highest number that goes up here. If I have the whole expanded form, it's really easy because this is 0, 1, 2, 3, and 4. And there goes my highest number here. So 0 to 4, and then I could double check this by like plugging in these values and seeing if I get the same thing, right? If I plug in 0, 0 times 4 is 0, plus 4 is 4. Then if I plug in 1, 1 times 4 is 4, plus 4 is 8. If I plug in 2, 8 plus 4 is 12. And you see that I come back to the same expanded form. So this here is one sigma notation that would work for the first one. And now when I am doing this, because I have all these numbers, I can go ahead and add these things by hand, right? Add those together and get 24. Those first 3 together to get 24. Then that becomes 40, and that becomes 60. So my actual sum for the first one is going to be 60. It's going to get a little bit more challenging when we get to C there, but let's move on to B first. So again, like I said, it becomes challenging if you don't recognize the patterns here, because in this one here, it goes up by 1, then it goes up by 2, and then it goes up by 4, and then it goes up by 8. So it's changing how much it is going up by, meaning it is not linear. So the issue with this here is that when I make my sigma notation, I set this equal to 0, then I need to figure out what I can create, what sort of equation I can create that if I plug in 0, it gives me 1. And then if I plug in 1, it gives me 2. I plug in 2 and it gives me 4, 3, and it gives me 8, 5. So again, because I'm a math teacher, it seems straightforward to me, but when I do this, it's going up. It's like multiplying by 2 each time. And whenever something is multiplying by 2, multiplied by 2, then that's not going to be a linear function, but what we call an exponential function, because it is multiplying by the same thing over and over and over again. And that means that my variable is going to be in my exponent. And so what you notice here is that if I were to plug in 0 for k, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16, 2 to the power of 5 is 32. And so that helps me give me my expression here. And when I'm going through this, I go ahead and goes up from 0, 1, 2, 3, 4, and 5. And there gives me my sigma notation. Now, again, I'm just going to plug these into a calculator, add them all together, and I get 63 as my sum for this one. But again, it's really the pattern recognition that becomes the hard part of these. Okay, so for the last one, when I'm looking at this, the first thing is I notice that it's going up by 2 each time, which is good. Nice me know that it is linear. So k equals 0. It's going to be 2k plus 2 because I'm starting at 0. I'm starting at 2. So that's my y-intercept here. My slope, since it's a constant rate of change, is 2. That's my slope here. And so that gives me my equation for the sigma notation. Now, the hard part in this one is figuring out what is going to be the final number. And basically in this one, what you can do is you can subtract the first and the last. So this is kind of like a math trick that is helpful. I take 200, I subtract 2, and I divide it by whatever the slope is or whatever the constant rate of change is. So in this one, 200 minus 2 is 198. Divided by 2 is just 99, and that's going to be my final number. So it's a helpful trick. It worked with the first one also. In this case here, when I went back to this one, 20 minus 4 is 16. The constant rate of change was 4. So my highest value, my top value there was 4. Works for the linear functions, not so much for the other ones, but this is a really good trick to help you. So in this one here, I'm not going to do this one by hand because that would be ridiculous. There's lots of numbers, 90 or 100 of them, I guess. And if I were to plug this into a calculator, I could do it with my sigma notation function, and then it would tell me my answer is 10,100 as the sum.